Hello everyone. So in this module, I will talk about one of the most important routine analytical tools of the synthetic chemist. Here I will talk about nuclear magnetic resonance spectroscopy, that is NMR. The NMR used to determine relative numbers and environments of NMR active nucleus, and it is used to investigate basically in the solution the dynamic behavior of the molecular species. Although frequently we used proton and carbon-13 NMR, there are many more nucleus are there that can be studied by this technique. Now, what is NMR? As you can see over here, the nuclear magnetic resonance. So this is a technique, this is a spectroscopic technique involving absorption of radio frequency, and thereby transition takes place from the ground level to excited level, and from this transition the data we got, thereby we studied the different and chemical properties, different chemical environment of different molecule. The magnetic environment of nucleus, it is affected by this resonance frequency, and it allows the structural information to be deduced. Now, which nucleus are NMR active, and how we can and know about their isotope abundance? So there are many nucleus, they have a nuclear property that is called spin. Now those nucleus which have this property nuclear spin, they are NMR active. So nuclear spin, which is nuclear angular momentum, is given by this quantum number I. So I can have different values like 0, 1 by 2, 1, 3 by 2, 5 by 2, like integer, half integer value. But if the value of I, the nuclear spin value for a nucleus is 0, so if the nuclear spin I is equal to 0, then that kind of nucleus is NMR inactive. For example, carbon 12. So this nucleus carbon 12, for this nuclear spin is equal to 0. So this carbon 12 is NMR inactive. For example, uh, proton like 1H. For proton nuclear spin, there is a nuclear spin is equal to 1 by 2. Carbon 13. Carbon 13 also nuclear spin I is equal to 1 by 2. So these two nucleus, proton 1H and 13C, they are NMR active. So basically, the principle I will talk about in the next slide. So basic understanding is that in the absence of magnetic field, the different nuclear spin state of a nucleus are degenerate. So when there is no magnetic field, this nucleus have degenerate energy state. Now when the magnetic field is applied, this energy level, they are split, becomes non-degenerate, and this allows the nuclear spin transition to occur when this radio frequency proper radiation which matches this energy level, and therefore that is absorbed. Now coming to the principle of NMR spectroscopy. So this is the energy level diagram of a nucleus having spin quantum number is equal to 1 by 2. By understanding this pictorial, you will understand the principle of NMR spectroscopy. So this is a nucleus having nuclear spin I is equal to 1 by 2. Now in absence of magnetic field, when there is no field is applied, there are two energy level, that is Mi is equal to plus half and Mi is equal to minus half, they are degenerate. They are degenerate. That is having the same energy level. Now you can see that this is the nucleus. It is electrically charged, and because it has intrinsic spin value, that is why it behaves like a magnet. So when the magnetic field is applied, here, you can see that these two energy level, it is split into different energy level. They are not degenerate anymore. So one of the energy level is that the direction of this spin is aligned with the external magnetic field. The magnetic field is applied in this direction, upward direction. So this is the direction of this magnetic field B naught. So this spin, so this spin Mi is equal to half plus 1 by 2. This is this energy level, and it is aligned to the magnetic field. And another is the higher energy level, where nucleus with higher energy level, that is here the you can see that orientation of the spin is opposite the external magnetic field. Magnetic field is applied along upward direction. This is the direction of the magnetic field, but here you can see that the spin is direction is opposite to the magnetic field. So this is the energy level Mi is equal to minus 1 by 2. So this energy gap correspond to the radio frequency. So this is the energy gap delta E, so which is equal to h nu. So when the radio frequency that is applied, it is matches with this nu, that is the energy gap between these two energy level, then resonance take place, and we can see the proton Nmr spectra, different kind of nucleus spectra, spectra. So once more time, so this nuclear spin is called alpha spin, and this opposite to the external magnetic field, this nuclear spin is generally called beta spin. So alpha spin is aligned along the magnetic field, and beta spin is aligned opposite to the magnetic field. And this energy gap delta E is equal to h nu. So this is the energy gap correspond to the radio frequency. Now how the system actually operates the NMR experiment. So basically, normally what happens is that in NMR experiment, the radio frequency is fixed. For example, 500 megahertz is instrument, 500 megahertz instrument. So here radio frequency is kept fixed, 500 megahertz radio frequency is given. Now what actually happens is that it varies the magnetic field strength. So if you change the magnetic field strength, you can see that the magnetic field is varied along this direction. This is the magnetic field strength. So when you increase or decrease the magnetic field strength, the energy gap delta E will become lower when the magnetic field strength is low, or higher when magnetic field strength is higher. So keeping the radio frequency fixed, for example 500 megahertz NMR instrument, keeping this radio frequency fixed, if we vary the magnetic field strength, then there will be a situation when the magnetic field strength corresponding to this energy gap delta E will matches the energy of this radio frequency that is provided from the external source, and that time only resonance takes place and we will get the NMR spectrum. Now coming to the nucleus, which having the nuclear spin value that only uh, responds to the NMR spectroscopy. So nucleus consists of protons and neutrons. So there is a general trend, or you can say tricks, to understand which nucleus are NMR active or which nucleus are NMR inactive. So when you can see that in the nucleus there is a even number of proton and even number of neutron, that case nuclear spin, that is I value, would become 0. For example, carbon 12, here proton number is 6, number of proton is 6, And number of neutron, you can see that 12 minus 6, that is 6. So even number of proton and even number of neutron, it will give a nuclear spin I is equal to 0. You can see the oxygen 16. So here proton number is how much? 8, and neutron number is also 8. So here also even number of proton and even number of neutron are there. That is because this type of nucleus are in our inactive, having I is equal to 0. Now there are nucleus which having nuclear spin value, or nuclear spin value having integer nuclear spin value, like 14 nitrogen 14. So here you can see that both the proton number and neutron number are odd. Proton number here is 7 and neutron number is 7. So here the I value is 1. So in this type of case, when the proton, both the proton number and neutron number are odd, in that case the integer value of nuclear spin will you will get. There is another type of scenario when one of the number is odd and another is even. For example, this kind of nucleus 1H carbon 13 19A, they having this kind of nucleus where there is one of the proton or neutron number is odd, they are having this nuclear spin of half integer value, 1 by 2, 3 by 2, 5 by 2. Among them, this kind of nucleus having nuclear spin of 1 by 2. For example, proton, carbon 13, 19F, 31 phosphorus, they having the nuclear spin is equal to 1 by 2. And the rest of the nucleus you can calculate by your own, where there is odd number of proton or uh, even number of neutron, or vice versa. They having this half integer like 1 by 2, 3 by 2, 5 by 2 value of nuclear spin. That is, they are in our inactive. So basically those nucleus having the even number of proton or even number of neutron, they are in our inactive, having I is equal to 0. These are some properties of selected in our active nucleus. Over here the chart is given. So you can see that the most popular is the proton NMR, the 1H nucleus, having natural abundances greater than 99.9%. You can see that which having the nuclear spin, this is I nuclear spin is equal to 1 by 2. The chemical shift reference, so I will talk about this later. So in different NMR spectroscopy like proton NMR or different NMR, so there is a chemical that should be present as a reference or internal standard. So normally in proton NMR, this tetramethyl silane SiMe4, this chemical compound is used as a chemical reference. Similarly, you can see that carbon 13 NMR, you can see that its natural abundance is very low, 1.1%, 1.1% compared to the proton NMR. You can see that, and it also have a nuclear spin value is equal to I is equal to 1 by 2, and same internal standard is used, is Me4 as of that of proton NMR. So because of this very low natural abundance of carbon 13, so normally in the proton NMR spectra we don't see any interaction of this proton with the carbon, that is carbon 13. In organic compound or any molecule, the proton is attached with the carbon, we don't see any interaction splitting because of this carbon 13. Generally we don't consider it because of its low natural abundance, that is 1.1%. We don't see any interaction. Similarly, other heteroatom NMR, you can see that like boron 11 boron, it also have this nuclear spin is equal to 3 by 2, nuclear spin is equal to 3 by 2, and natural abundance 80.1%. Similarly 19F, which also nuclear spin value is equal to 1 by 2. Similarly, there are different heteronuclear NMR that is possible to study, that is possible to record, having this natural abundance value it is given, and this is a frequency. For example, proton NMR refer to 100 megahertz. Compared to this, different nuclei are given their radio frequency range. For example, if you set a radio frequency 100 megahertz, will selectively give the proton NMR signal, not the other nuclei will respond, will give the peak. Similarly, if you change the radio frequency to different level, for example this level, then it will selectively detect this fluorine 19F fluorine in the species, in the molecule, not proton NMR. So this radio frequency is selective for particular nucleus. I will talk about this in the later also. Now, which nuclei are suitable for NMR studies? So there are different criteria for nucleus or for the NMR spectroscopic studies. So as I have already said, a wide range of nuclei may be observed, may be recorded by NMR spectroscopy. But the inherent property of some nuclei, for example large quadruple moment, make their observation difficult. So first point is that nuclear spin or nuclear quantum number, that is I value, should be greater than equal to 1 by 2. So if the nucleus having nuclear spin quantum number is equal to 1 by 2 or greater than 1 by 2, that kind of nucleus are active. You can study in the NMR spectroscopy. For example, if nuclear spin I is equal to 0, that nucleus is NMR inactive. Secondly, it is advantageous for the nucleus to occur in a significant abundance. So natural abundance actually important for the NMR also, because isotopic enrichment may be used to improve signal to noise ratio. If the natural abundance is higher, then it will improve the signal to noise ratio. Although carbon 13 NMR, in carbon 13 nucleus, we all know that because of its very low abundance 1.1%, although it is extensively used for NMR spectroscopy. So in that case, there are different parameters we have to tune in order to get the good spectra. And third point is that relatively short spin relaxation time. This is very important. This third part, that is the relatively short spin relaxation time, that is actually written as tau 1. It should be relatively short. Now this relaxation time, this property not always depend on the nucleus itself, but also it actually depends on its molecular environment. In the molecule, the surrounding environment of this nucleus, it actually affects this spin relaxation time tau 1. Now some elements having more than one isotope, and those isotopes are also NMR active. Now it will depend the inherent property of the nucleus of those nucleus having relatively lower tau 1 value. For example, I will say that lithium 6 and lithium 7, these two isotopes in our active. However, lithium 7, this nucleus have a spin relaxation time is equal to like less than 3 seconds. Whereas lithium 6, this nucleus having relaxation time is equal to 80 to 100 millisecond. 80 to 100 second. 80 to 100 second. So if you compare these two tau 1 value, so it is appropriate for NMR spectroscopy to observe the lithium 7 nucleus. So this nucleus, that is lithium 7, is thus more appropriate for NMR spectroscopic observation, and this is the also favored because of this natural abundance is much more higher than lithium 6. So natural abundance also lithium 7 is that 92.5%. 92.5%. As you can see that this chart I have also given that 92.5% is natural abundance of lithium 7. Although lithium 6 is also nuclear active, NMR active, but lithium 7 is preferred because of this relatively lower relaxation time and also the higher natural abundance value. Radio frequency and chemical shifts in the NMR. Now, particular nucleus, for example, proton, carbon 13, 31 phosphorus, they absorb characteristic radio frequencies. That is, they resonate at a particular frequency. So, if in our instrument is tuned to a particular resonance frequency, only selected NMR nucleus will be observed, giving signal. For example, if the NMR instrument is tuned at 400 megahertz frequency, then only proton gives a signal. Similar to the same instrument, if it is retuned to 162 megahertz frequency, the 31 phosphorus giving the signal, that is, they are observed. So it is important, this is analog, so you can understand by this manner that this is analogous to tuning a radio station and receiving only one station at a time. You can understand by this manner. So in 1H NMR experiment, proton will be in different chemical environment. There will be different proton, many proton will be attached with carbon and other nucleus, and they, not all the proton will give same frequency, will be resonate at same frequency. There will be some will be resonate at different frequency. The same is true for also other nucleus like carbon 13 and 19F in 19F nucleus. So in a molecule, when there are proton, there are carbon, fluorine, the radioactive element are there. So never active, sorry, not radioactive, never active any elements are there. They will be resonate at different frequency. Not all the time they will resonate at same frequency. So each signal in an Nmr spectrum is denoted by a chemical shift value delta, a value that is given relative to the signal observed for a specific reference compound. So you can see that this is the chemical shift delta. It is given as frequency difference, that is frequency of your targeted signal, that is nu of your desired proton or desired innovative nucleus, that signal minus radio frequency, that is the signal coming out from the reference. For example, proton NMR, carbon 13 NMR, it is tetramethylsilane TMS. So this difference delta nu divided by the radio frequency, that is given for the reference compound, specific reference compound. So basically a value that is given relative to the signal observed for a specified reference compound. Now the frequency difference delta nu in it is normally calculated in hertz between the signal of interest, that is nu, and the some defined reference compound, for example tetramethylsilane nu 0, and it is divided by the absolute frequency of the reference signal. Normally in order to get a small number, and this delta according to IUPAC is given over here. It is written as this frequency difference divided by this radio frequency of the reference compound. It is multiplied into 10 to the power 6, and this value then come in this ppm range, parts per million. So this parameter delta, that is chemical shift, this parameter is independent of applied magnetic field strength, and you can see that for the same proton in a molecule, if you record the NMR spectrum in different instrument, for example 400 megahertz, 500 megahertz or 800 megahertz, all the time you will get that same chemical shift delta value in ppm. So this value, chemical shift delta, it is invariant of the applied magnetic field. There is another point. So when the NMR spectrum is recorded, the signals are coming out for a particular nuclei are said to be shifted with respect to the standard reference signal. When this shift is positive compared to the reference, it is called that shifted to higher frequency. When this shift is negative or less positive, that is a relative term, it is called this frequency shifted to lower frequency. So there is a terminology to understand to suggest uh, this phenomena. So when this positive delta value suggests, when the signal coming comparatively positive delta value or higher range delta value, it is suggested downfield shift. When this chemical shift appears as comparatively negative or low delta value, then it is called upfield shift. So you can understand. So in the NMR, it is like looks like this. So it starts from here 0, from left to right. It is like increasing value of chemical shift 0, 1, 2, 3, like here 4, 5. You can see 10. So this is the chemical shift region. NMR is interpreted according along this direction. Normally it is happening. So at 0 ppm, normally the reference standard is observed, TMS. Delta is equal to 0. The reference standard molecule is observed at delta is equal to 0. Now there is also negative part, -1, -2. So when there some peak, when there some peak, when there are, for example, there is two peak is appearing, one around 2, one around 2, and one around, for example, -1. So one is delta value is 2, one is delta value is equal to -1. So this peak, this proton which falls in delta is equal to, it is called, it is downfield shifted, and this proton which is the negative region or comparatively low delta value region, it is called, this proton is upfield shifted. Now this downfield shift or upfield shift, it can also be understood by another term, that is shielding and deshielding. When the nucleus is shielded, when the nucleus is surrounded by electronically enriched atom that push electron density to that particular Nmr active nucleus, in that case that nucleus is shielded and it gives upfield shift. For example, and another case, when particular nucleus, Nmr active nucleus, is attached to electron negative groups or some electron withdrawing groups which pulls out the electron density from that nucleus, then that nucleus is said to be deshielded and it falls in the downfield shift region. It gives a signal which is comparatively to higher delta value region, and that is called downfield shift. Now coming to chemical shift ranges. The range of chemical shifts over which Nmr spectroscopic signal appear is depend on the nucleus. So it is a nucleus depending phenomena. The most commonly observed nucleus is proton 1H, and in organic compound the spectral window is like 0 to 15. So this is the diamagnetic region. So 0 to 15 ppm. So most of the proton falls in this region for a diamagnetic compound, like in organic compound. Inorganic compounds, the window may be widened for proton nucleus attached to metal center are to be observed, or if the signal are paramagnetically shifted. So this is very important part. I will come to at the later part, when some metal, paramagnetic metal, is attached to the proton or not directly or indirectly attached in the vicinity of the proton, it will impact the chemical shift region range of that nucleus. It will be not within this region 0 to 15. The range will be much widened. I will talk about in the latter part. The chemical shift range for other NMR active nucleus, for example, carbon 30, is typically 50 ppm to 250 ppm range, and for 30 on phosphorus, it is given like plus 300 to minus 300, 300 plus 300 to minus 300, plus 300 to minus 300 ppm for phosphorus NMR, 30 on phosphorus NMR. For selenium NMR, for example, it is plus 200 to minus 1000. It is plus 200 to minus 1000 ppm. So you can see that. So the spectral range actually depend on the NMR active nucleus. For proton, it is different. For carbon 13, for phosphorus, selenium, it is different. Now coming to solvent, which solvent is used for studying this NMR spectroscopy. Sample for solution NMR spectroscopy are generally prepared. So basically NMR is a solution state study. This solution state property can be understood, can be detected by NMR. It is a solution state property. So the deuterated solvent is used. So important point is that NMR, your compound, your molecule should be dissolved in the deuterated solvent. Example is given, most widely used CdCl3, that is chloroform, deuterated chloroform. Then CD3CN, CD2Cl2. So basically, first you have to check the solubility of your compound. If your compound is soluble in a particular solvent, you have to use the deuterated solvent of that solvent. For example, if your compound is soluble in chloroform, you have to use CdCl3 to dissolve your compound and record the NMR. So one of the reason for this that it is simple that non-deuterated solvent, why deuterated solvent is used. So basically non-deuterated solvent is used because in 1H NMR spectroscopy experiment, the signal due to the solvent would swarm those peak due to the sample. So if your molecule, if your complex containing a peak that is coming at the same chemical shift value of the solvent, then it will be interfering. So basically that is why deuterated solvent is used. That non-deuterated solvent in proton NMR spectroscopy experiment, that signal due to the solvent would swarm those due to the sample. The remaining unlabeled compound provides a useful interference signal in orange NMR spectrum of the sample under study. Normally, typically deuterated solvent that are provided commercially available, they are actually 99.5% like deuterated level, 2H, for example 2H level incorporated. The remaining part, unlabeled compound, that gives that internal reference signal in the 1H NMR spectrum of the sample under study. Under normal condition, NMR spectra, the ratio of peak areas, that is the integrals of the signal in the spectrum, is proportional to the number of nucleus giving rise to that signal. For example, you can take that example HCCH3. So there are two types of proton. One is this HA and this HB. So if you record the NMR of this compound, you will see that the NMR spectra, it will look like this. And if you take the integral, you can see that So this peak, small peak is for 1 proton and this peak is for 3 proton, like it is just 3 times higher than that of the small peak. So basically the peak area, if you calculate the peak area, you can see that small peak is for this HA proton and this large peak is for the CH3 proton, and the ratio is equal to 1:3. It suggests that there is 1 HA proton is there and 3 HB proton is there. Now there is one important note. This integration of the signal must be treated very cautiously, since this peak integration is depend upon the relaxation time, again the tau 1 of the nucleus in question, that is the time taken for the nucleus to relax from the excited state to ground state during the Nmr spectroscopic time measurement experiment. So for this particular problem, the relative integrals of signal in a carbon 13 Nmr spectrum. So the point is that carbon 13 Nmr, you cannot integrate the peak like carbon peak because of this relaxation time, because carbon 13 Nmr, the different carbon 13 Nmr, they have relaxation time, different relaxation time. You cannot integrate that carbon 13 Nmr. For proton, you can integrate the proton Nmr spectra and you can calculate the relative number of protons present in the molecule. So basically the problem, it is because that signal broadening. So signal is broad, and because of the signal broadening, one cannot integrate the signal. And what is the reason? Basically the signal broadening coming because of different reason, chemical factor, also the intrinsic factor. Signal arising from proton attached to, for example, nitrogen atom, they are very broad in nature due to the quadruple relaxation by this 14 nitrogen 14 nucleus, which have the nuclear spin is equal to 1. Exchange with solvent protons also causes broadening. For example, ethanol, it is rapidly exchange this alcoholic proton with the water molecule, and because of this rapid exchange with the solvent molecule, this OH peak is very broad in nature, sometimes very broad in nature, and thereby this kind of peak cannot be uh, integrated because of this broadness in nature. Now the important part I will talk about here is that homonuclear spin-spin coupling. Here I will talk about the 1H coupling, which is very important in order to understand the splitting pattern in the proton Nmr spectrum. This is 1H coupling, homonuclear spin-spin coupling. So in a 1H nucleus, having nuclear spin is equal to 1/2 may be in of the two spin state. As I have already mentioned that proton having nuclear spin is equal to 1/2, they have two different spin. One is aligned with the external magnetic field alpha, one is opposite to the external magnetic field, that is called beta, and there is the external magnetic field B0. And this energy difference between the spin state depends on the applied magnetic field of the Nmr spectrometer. So this energy difference actually dictated by this external magnetic field. How much you put the magnetic field, it will vary the delta E value. For example, you arbitrarily consider a molecule having HA proton which is connected to another proton HB through chemical bond. Through chemical bond, they are connected directly, like one bond away or more than one bond away, like directly or indirectly they are connected to chemical bonds. Now these HA and HB are magnetically non-equivalent, therefore it will give different chemical shift value. The delta A and delta B will be different because of their magnetically non-equivalent. Now local magnetic field generated by the spin of HA. So HA the local spin orientation of this HA is not detected by HB. If it is the possibility, then HB will give a single line spectrum. So if HB cannot influence the two different energy level, that is plus up minus up spin of this HA proton, it will give a single line spectrum in the NMR. For HB you will get single line. Similarly, if HA cannot influence, cannot affect, cannot experience the different spin state, different spin level of HB, it will also give a single line spectrum in the NMR. For HA, you will give a single line proton NMR spectrum. But the second scenario is that if HA is affected by the magnetic fields associated with HB, vice versa also, HB affects the magnetic fields of HA, then the proton NMR spectrum of HB will not be a single line, it will giving a two line spectrum, and it is called doublet. Similarly, HB also give two line spectrum, and it is called doublet. This single line spectra splits into two equal lines of same intensity, and it is called doublet line. So therefore in the NMR spectra you will get, therefore in the NMR spectra you will get two doublet line, one correspond to HB, one correspond to HA. So two doublet lines you will get, for example this is for HA, this is for HB. So two doublets you will get, and the separation between these two lines is very important. This difference, this separation between these two lines is called coupling constant J, which is calculated in Hertz. So this separation between these two line doublet is called Hertz, coupling constant J, and it is measured in Hertz. In general, coupling to one proton gives a doublet, to two equivalent proton gives triplets, and similar manner you can calculate that. For example, a single proton coupling give when there is no adjacent proton, it gives a single line, there is no interaction. When there is one proton interact with another proton, one proton, then it will give a doublet. When there is two proton, it will give a triplet. When there is three proton, it give a quadruplet. In this way, this is called Pascal's triangle. From Pascal's triangle you can calculate the number of line and their relative intensity. For example, for doublet it is 1:1 intensity. Intensity is 1:1. You can see that two height are similar, same. For triplet you will get a 1:2:1 pattern. It is 1:2:1 pattern. In quadruplet you will get 1:3:3:1, this kind of pattern. So this is a relative intensity, and there is a general formula from which you can directly calculate the number of lines, that is the multiplicity of the proton, that is given by 2ni plus 1 formula, 2ni plus 1, where n is the number of nucleus that you are calculating, I is the nuclear spin of that nucleus plus 1. So 2ni plus 1 is that I is the nuclear spin of that nucleus. For example, proton nuclear spin is 1. N is the number of nucleus that are affecting, that are actually causing the splitting. For example, here HA causing the splitting of HB, similarly HB causing the splitting of HA. So here n is equal to 1. So if you calculate by this analog, 2 into n is equal to 1, I is equal to 1/2 for proton plus 1. So then you will get number of multiplicity is equal to 2 line, and that is why you are getting this doublet. And lastly, one important point is that this coupling constant, in this case, when for example, two proton HA and HB, they are adjacent to each other, like they are close to each other, they are adjacent, they are directly attached, they are adjacent to each other, then the coupling constant J for HA and HB will be same, exactly same value. that Aj causes the splitting of Hb and Hb causes the splitting of Ha. In that manner, in that case, coupling constant of Ja and JB, that these two coupling constant will be is equal to same value, will give a same value. So by this manner you can understand the relative position of that proton in a molecule. In a molecule, if the two protons are adjacent to each other, they will interact, they will split the each other line and giving the exactly same coupling constant value. So by looking the coupling constant value, you understand that the position of this kind of proton in the molecule. Now take us some example and understand the NMR spectra, like how we can understand interpret NMR spectra experimentally. So this is the 1A spectrum of the butanol. So if you know the structure, you know you can draw like this: CH3, CH2, C double bond O, CH3. So first you have to understand how many types of proton are there in this butanol. So you can easily understand that this CH3, it is a one type. For example, you can mark this is HA adjacent to CO. This CH2, it is in between this CH3 and CO. This is, you can mark HB, and this is terminal CH3. It is HC. So there are three types of proton A, B, C are there in this butanol molecule. So obviously you will get three signal for three different type of magnetically non-equivalent proton. Now NMR spectrum, you can see that there are three sets of line. Now which is one and how the splitting is coming. I've already discussed how the homonuclear splitting you can calculate using 2Na plus 1 formula. So you can see that this HA proton CH3 adjacent to CH3, there is no proton is there. It is directly attached to this carbonyl group. So there is no proton which can couple with this CH3. So it will give a singlet. You can see that this proton, there is no splitting is there. This is for HA. This is for 3 hydrogen atom. For CH2, you can understand that it is adjacent to carbonyl, which cannot split this Hb proton, but this CH3, that is HC proton, which can influence, which can interact with this Hb proton and couple and give the splitting. Now how many line will be possible for this Hb proton? You can see that you can apply the 2Na plus 1 formula. 2 into n will be 3. This Hb proton will be coupled with 3 Hc proton, so n will be 3. For proton I will be 1 by 2 plus 1. So you can see that you will get 4 lines. You will get 4 lines, that is quadrate. Intensity will be 1 is to 3 is to 3 is to 1. So basically you will get a quadrate. So you can see that there is one spectrum is there. So you can see that this is 1 is to 3 is to 3 is to 1. So this is the quadrate. So this is the Hb proton. So basically this is Hb proton. Hb proton. This is Hb proton, and it is splitted 1 is to 3 is to 1 quadrate. Similarly, you can calculate that CH3. This CH3, that is Hc proton, it will be coupled because of this Hb proton and giving rise this triplet. And intensity will be according to Pascal triangle 1 is to 2 is to 1, 1 is to 2 is to 1. Here is that 1 is to 3 is 3 is to 3 is to 1, and here will be singlet. So it will be giving a triplet. According to 2ni plus formula, you can apply by yourself, and you can see that this Hc proton, this is for basically Hc proton. It gives a 3-line spectrum because coupling with this 2 Hb proton. So now we can understand how to interpret the organic sample proton and their homonuclear coupling. Case study 2. This is 31p Nmr spectrum of PF6 minus salt. This is one of the inorganic salt. You can see that the structure is given over here. This is a octahedral molecule, octahedral structure. And if you want to record the 31 phosphorus Nmr spectrum, you will get a spectra like this, having binomial septate, having this septate line, septate. Now, how come these lines are coming? You can directly calculate the number of line using the similar formula. Multiplicity is equal to 2ni plus 1. So here you can apply the formula 2ni plus 1 formula. So you can see that you are want to record the 31p Nmr. So there is one 31p Nmr, and it is connected with 6 fluorine atom, and this fluorine atom, that Nmr active 19F fluorine, which have the nuclear spin value is equal to 1 by 2. So there are 6 fluorine which connected with phosphorus, which causes the splitting of this phosphorus, having nuclear spin is equal to 1 by 2 plus 1. So then you can calculate that it will give a 7-line spectrum, and it is according to the Pascal triangle. You will get the intensity ratio also from the Pascal triangle, and gives like this septate line, septate spectrum. Now the one important point is that separation, peak gap, it is called the coupling constant J. JPF means that coupling between this phosphorus and fluorine, and you can see that this is a very large value of coupling constant, 708 hertz, which actually suggests that there is a direct attachment of this fluorine nucleus to the phosphorus atom. So this kind of coupling constant, understanding this coupling constant by looking the coupling constant, one can understand where there is a direct coupling or there is long range coupling. So in this scenario, there is only one type of coupling is possible, PF coupling, 708 hertz. So in another molecule, if there is coupling like small coupling, PF value, then you can say that there is a long range coupling may be possible, may be observed, because direct coupling is so strong, so much strong here. So it is possible to observe long range coupling also in the molecule if there is another phosphorus atom is present or fluorine atom is present, which is not directly attached to the phosphorus atom but covalently attached to some other atom and one or two bond away from this phosphorus atom. And you can see that this Nmr spectrum is recorded at this radio frequency 162 megahertz radio frequency, which I have already told earlier that this is very specific for 31p Nmr. In the molecule, if there is proton, it will not be giving signal, because this 1h megahertz actually causing the transition for this phosphorus, 31 phosphorus nucleus only. So this is very important. Nmr spectrum of this salt PF6 minus containing a binomial septate, and this binomial septate value can be obtained, can be understood by this Pascal triangle formula, Pascal triangle chart. Now this is a very good example, and you understand one important concept from here. 99 Nmr. This is the 99 Nmr, and it is recorded in this Nmr instrument having 376 megahertz radio frequency. This is the 99 Nmr spectrum of this inorganic molecule XCF5 minus. So this is a planar molecule XCF5 minus molecule. You can see that there is five fluorine atom attached to the xenon nucleus. So you want to calculate, you want to understand, to record that 99 Nmr. So for that, important is the what is the nuclear spin of this xenon atom. What is the nuclear spin of xenon atom? You have to understand, you have to know that I value of xenon, then only you can calculate the splitting and other thing. So both the fluorine and xenon atom having NMR active nucleus having I value is equal to 1. So I value of xenon is equal to 1 by 2, and its natural abundance is 26.4%, and for fluorine atom 19F fluorine, it is also 1 by 2, but it is a 100% natural abundance. So important part is that the xenon atom, which is nuclear active, it has only 26.4% natural abundance. So this is an important part. The isotopic abundance of xenon 129, that is the nuclear spin I is equal to 1 by 2, that is the only NMR active xenon nucleus having 26.4% natural abundance, and the rest of the xenon, that is NMR inactive, I is equal to 0. Now the Nmr spectrum of XCF5 minus is shown over here. You can see that now you can see that there is 3-line spectrum in the spectrum. You can observe. So this single line, this is because all the fluorine atom are chemically equivalent, magnetically equivalent, and they are attached with the xenon atom, this giving this single line spectrum, with the xenon having this kind of this percentage 73.6%. So basically, so those xenon atom having nuclear spin is equal to 0, so they will not interact with the fluorine atom, they will not split the fluorine atom signal. So those, because of those xenon atom, they have higher natural abundance, it gives a single line spectrum of these 5 fluorine atom, and along with that you will get a 2 doublet, because of that remaining 26.4% xenon atom having nuclear spin I is equal to 1 by 2. Thereby, according to 2Ni plus 1 formula, you can calculate there is 26.4% xenon atom. Here there is only one atom, and having spin value is equal to 1 by 2 plus 1, you will get a doublet, 2-line spectrum. So, and this is because of this xenon fluorine coupling. This JXFE is very large. You can see that 3400 hertz. This doublet is arising because of that nuclear NMR active xenon atom having natural abundance 26.4%, giving this shorter signal, shorter height. You can see that, and this is the coupling constant. So you may mistakenly interpret this is a triplet of 1:2:1, but this is not a triplet. This spectrum can be interpreted in terms of a singlet. The central line is equal to singlet plus doublet, plus a doublet. So this spectrum can be interpreted in terms of a singlet, the central line, this central line, and it is due to this 73.6% abundance of the xenon molecule, xenon atom, that is having nuclear spin is equal to 0, which will not couple the fluorine atom, 19F fluorine atom, plus an overlapping doublet due, plus this overlapping doublet, these two lines, this is a doublet which is due to the coupling of this 129 xenon. Now if you calculate the center of these two doublet, which actually falls in this region, which actually the single line, the center of the doublet coincide with the position of the singlet, and it is actually happening because all the 19F nucleus resonance at the same frequency, and these two small peaks, basically these two small peaks shown over here, the doublet, they are actually called satellite peaks. So this is very important term. So these two side peaks are called satellite peaks. So this 19 NMR, you can see there is many more thing to understand. One is that the central singlet line that is appearing because of the 5 fluorine atom, they are non-interacting with the xenon atom, because most of the xenon atom 73.6% are I is equal to 0. They are giving this single line spectrum, and the rest 26.4% xenon atom, which is new in our active I is equal to 1/2, it splits this 5 fluorine atom and giving this doublet spectrum, and these two side peaks, they are called satellite peak. Coming to the case study 6, this is a very easy example. Again 31 phosphorus Nmr spectrum I have taken to explain these two molecule chemical changes. As triphenyl phosphine PPH3 and this oxidation part, triphenyl phosphine and this phosphine oxide. So this is the 31 phosphorus Nmr taken at around 162 megahertz radio frequency. So you can see that the PPH3 molecule in the phosphorus Nmr, you will get Nmr signal around -5 ppm. But when the molecule is oxidized to phosphorus oxide, phosphine oxide, the phosphorus Nmr actually getting very shifted, very downfield shifted. This is called downfield shift. This is called downfield shift. From -5, it is around +25 ppm. So now it is -5 ppm. So you can see that. So there is only one phosphorus atom. For that you are getting only one line, and it is actually decoupled with the proton. So there is no proton phosphorus coupling. So a shift to more positive, that is higher frequency, generally accompanies the oxidation of tertiary phosphine. So this is actually good technique, Nmr technique, by which you can understand by carrying out a reaction if your starting molecule is triphenyl phosphine or triphenyl phosphine oxide. So 31 Nmr spectrum of a phosphine is very important to record, because before use in the laboratory is an easy way of checking the purity of the phosphines which are readily oxidized in air. So from the Nmr spectrum, actually we can understand the purity of a molecule, purity of the complex we are synthesizing, we are using in a chemical reaction. So if this phosphine is oxidized, you will get a Nmr phosphorus Nmr peak around 25 ppm, very downfield shift. When it is tertiary phosphine, you will get a Nmr spectrum around this -5 ppm range, negative range. So from this Nmr spectrum changes, one can understand the chemical reaction pathway, and also the mixture. If the Nmr spectrum consists of both the peaks, like +25 ppm or -5 ppm, that means that it's having a mixture of two compounds. that some of the part is oxidized to oxide and rest is remaining the tertiary phosphine. So this is very important to understand the purity of a compound using Nmr spectroscopy. So I'll conclude this session with the important topic and illustration example, that is paramagnetic Nmr. Although paramagnetic Nmr cannot be explained in a single slide, but I will just give a small overview of paramagnetic Nmr with the one example. Now paramagnetically shifted 1H Nmr spectrum. Paramagnetic compound, they are having unpaired electron, one or more than one unpaired electron, and this unpaired electron, this electron spin has a significant consequence on the 1H Nmr spectrum of the compound, because they impart a local magnetic field arising from this unpaired electron or electrons on the paramagnetic center with the proton attached or the surrounding with this paramagnetic metal center. So this contribute to the energy difference between this nuclear spin state to fluctuate, to change the nuclear spin state energy level, and as a consequence the chemical shift value range for the proton NMR signal is much larger than in a diamagnetic compound. We know that for proton NMR spectra, the diamagnetic compound, the range is 0 to 15, but in the paramagnetic NMR spectra the range is very much widened, like it can be as up to as plus 1000 to minus 1000 ppm also. So in a paramagnetic compound there is additional factor, a large local magnetic field which arising from the unpaired electron spin density on the paramagnetic center. This will contribute to the energy difference between the two nuclear spin state of the proton, and as a result that chemical shift value will deviate from the normal diamagnetic range value. The second significant changes you can observe in a paramagnetic NMR is a broadening of the signal. So this is very important. The paramagnetic NMR naturally they are very broad in nature, and why is it so? And this is because of the significant shortening of the excited state lifetime, that is the relaxation time is very short. Because of the unpaired electron density, unpaired electron over metal center, they can relax quickly the higher energy spin state. So tau 1 is very low, and therefore the peak broadening you will get very broad peak you will get, very broad peak, broad in nature. So in some cases also the broadening is so much high that you will not get any resolved hypervalence splitting signal in the NMR spectrum. Normally in the diamagnetic organic compound, you can understand the spin coupling splitting, because the NMR spectra are quite sharp in nature. Because in case of paramagnetic NMR, because of its broadening in nature, broadness in nature, because of this small relaxation time, you will not get the information of the spin coupling between the proton molecule, between the proton nucleus. So there is advantage and disadvantage in paramagnetic NMR also. Now this is one example is given. This is cobalt 2 complex and the ligand is 110 phenanthroline. It's a paramagnetic center of cobalt 2 having unpaired electron 1. Now you can see that in the molecule how many different type of proton are there. So first you calculate the number of proton. So you can see that there is one type of proton, this HA, this is also HA, this is HP, this is also HP because of the symmetry, this is HC, and these two protons are similar because of the symmetry. So there are four different type of proton are there, which in the ligand part, which is attached to this metal center cobalt plus 2 having one unpaired electron. Now you can see that in NMR spectrum there is 4 line as you have expected, there are 4 different proton are there, but you can see that chemical shift value, delta value, which is given in the ppm, this is very downfield shifted compared to the normal proton value. Normal aromatic proton, benzene proton, you will get around 7 to 8 ppm or 9 ppm. But in this range, in this case, when this aromatic proton, this phenanthrolene proton connected with this cobalt 2, it is shifted as low as high as 50 100 ppm. Now we can see that this Ha proton, because it is much closer to the cobalt center, and it actually influence, actually having this unpaired electron density, so uh, like it is quite shielded, so you can say that this is Ha, this proton correspond to Ha. Similarly this Hb, and another is Hc, and that Hd proton, which is actually much more longer, much more, the distance between the metal center is high, so it cannot influence that much of cobalt 2 center unpaired electron density, so it is quite shielded. So that is why this can be Hd proton. Although detailed analysis, the detailed prediction, it cannot be done in a simplistic way, but paramagnetic NMR, you can see that chemical shift value is much more widened compared to normal proton NMR spectrum, because of this presence of metal center, and this NMR spectrum is quite broad in nature. You can see that this NMR, there is no spin splitting, there is no 1H homonuclear coupling is observed, all are singlet, as you can see over here. But it is expected that this HA should coupled with HB giving doublet, this HC should coupled with HB giving lies, giving this doublet, this multiplet signal. So multiplicity is absent in this kind of NMR spectra because the broadness in nature, and this broadness is coming because of this small relaxation time, very short relaxation time tau 1. Thereby in the paramagnetic NMR mostly you will not get that hyperfine spin coupling, spin coupling, splitting pattern. Thank you. In the next talk, I will discuss some other spectroscopy which is important to understand as an experimental uh, uh, study.